Second lecture on the method of electrical images. Today we consider a point charge in front of a grounded conducting sphere. We consider a sphere which is grounded, a grounded conducting sphere of radius a. The radius of the sphere is a, in front of a point charge q, which is at a distance d from the center of the sphere. Due to the presence of this charge, charges will be induced on the sphere. The density or the surface density of induced charges will be greater over here and will be a minimum over here, because this point is the nearest to the inducing charge and this is the farthest from the inducing charge. And if we want to find out potential at a point outside the sphere, we use the method of electrical images. Before going to that, let me first fix up the coordinate system used. The calculation becomes very much simplified if we choose the z-axis to be the line joining the center of the sphere and the point A or at which the inducing charge is located. In that case, what will happen is this is the sphere and this is the inducing charge. If we consider a strip, this is the sphere, we consider a so we are considering this strip. If this is be the z-axis, then moving from one point to another point is only the phi changes. If we move from one point to another point on the strip, only the phi changes, and because all the points on this strip are equidistant from the point inducing charge, the same charge will be induced on the strip. That is to say, the system will have an azimuthal symmetry. So to simplify mathematics, we choose z-axis to be the axis which is obtained by joining the center of the sphere and the location of the induced charge. So the coordinate of the inducing charge is d00 in a spherical polar coordinate system. If we are interested in finding out the potential at a point outside the sphere, so we must, as per the method of images, we must place the inducing charge within the sphere. Let q prime be the magnitude of the induced charge. Q prime is the magnitude of the induced charge and it is located at B, whose coordinate is d prime 0, 0. We want to find out potential at an external point P. We choose our coordinate system in such a way that this line, the z-axis, and the point of observation, that is OP, lies in xz plane. That is, it is the phi is equal to 0 plane. So our point of observation lies in phi is equal to 0 plane. This simply simplifies the mathematics. So the potential at P, potential at r theta, is the potential over here due to this charge. So this is kq r minus k d plus k q prime r minus d prime vector. If we write it in magnitude form, this part is r square plus d square minus twice r d cos theta to the power half, where theta is this angle, and plus r square plus d prime square minus twice r d prime cos theta to the power half k q prime. Now let me state you the boundary condition of the problem. The boundary condition is, firstly, phi e at r is equal to a is equal to 0. This is because of the fact this is a grounded conductor. The conductor surface is an equipotential surface, and furthermore it is grounded, so it is a 0. This is the first condition. Second condition, for all points except A, where Poisson equation is satisfied. And thirdly is phi e as r tends to infinity goes to 0. These are the boundary conditions of the problem. Now what is the potential at r is equal to a? Phi e at r is equal to a theta is 0, and this is kq by a square plus d square minus twice ad cos theta to the power half plus kq prime a square d prime square minus twice ad prime cos theta to the power half. Now you see that as per assumption the point E lies outside the sphere, so D is greater than A, and we are interested in finding out the potential outside the sphere, so the point charge must lie within the sphere. D prime is less than A. So we expand this like D is greater than A, so this is plus the other term. In this term A is larger than D prime, so we take k q prime by A common, plus higher order term. This relation is valid for all values of theta. Basically, this is Legendre polynomial of order 1 and this is Legendre polynomial of order 2. The result is valid for all values of theta. That is to say, this is an identity in Legendre polynomial. That is, the coefficient of every order of Legendre polynomial must be the same. That is, if we compare the coefficient of Legendre polynomial of 0, say P0 of x is 1, P1 of x is equal to x, and P2 of x is equal to 3x square minus 1 by 2. So this is P0, this is P1, this is P2. So the P0, the coefficient of P0 gives us The coefficient of P0 gives us K is common, so we forget about K. So K is the A1 upon 4 pi epsilon naught, the SI factor. P0, the coefficient of P0 gives you gives us Q by D plus Q prime by A is equal to 0, which immediately gives us Q prime is equal to minus AQ by D, which gives us the magnitude of the image charge. Now the coefficient of P1 gives us coefficient of QA. This gives us QA by D square plus, from here we get Q prime, Q prime A, Q prime D prime by A square is equal to 0. So if we write the value of Q prime over here, we get D prime is equal to A square by D. As per our assumption, D is greater than A. That means the magnitude of Q prime is less than the magnitude of Q, because A is smaller and D is larger, and from this we get D prime is less than A. So indeed the image charge lies within the sphere. So we can now say that this is the value of the potential at any point with Q prime is equal to minus AQ by D and D prime is equal to A square by D. This is the potential. So the calculation of potential is concerned, it gives you the potential. If you now want to find out the component of the electric field, the component of the electric field is obtained by as this. ER is equal to minus del phi E del R. If we differentiate this, the denominator will be R square plus D square minus twice RD cos theta to the power 3 by 2, and this part will be KQ R minus D cos theta from this part, and from this part it will be KQ prime R minus D prime cos theta R square plus D prime square minus twice R D prime cos theta to the power 3 by 2. This is the radial component. ER. E theta is minus 1 upon R del phi E del theta. If we differentiate it, it will be the denominator term is the numerator is differentiation of this with respect to theta. That will give us 2 will be cancelled with the half factor arising from this. So this is RD sine theta. This minus sign will adjust with this, and this R will be cancelled with this. So this would be KQ D sine theta, and the similar term is KQ prime D prime sine theta divided by R square plus D prime square minus twice R D prime cos theta to the power 3 by 2. If we want to find out what is the force that acts between the sphere, induced sphere, and this, it is the force between q and q prime where the separation is d minus d prime. So force is simply 1 upon 4 pi epsilon naught q prime, and the separation is ab square. So this is equal to d minus d prime. This is the force that acts between the induced conductor and the inducing charge. Now the surface density of charge. Surface density of induced charge. Surface density of induced charge, we know if it is big sigma, it will be a function of theta only. It is epsilon naught ER at R is equal to A. So this is the expression for ER. We put it as with R is equal to A. So it is a square plus d square minus twice AD cos theta to the power 3 by 2 to the power 3 by 2. In the numerator we will have kq k epsilon 0 q, and from this part a minus d cos theta, and from the second part we will have k epsilon 0 q prime a minus d prime cos theta with a square plus d prime square minus twice a d prime cos theta to the power 3 by 2, where q prime and d prime are given by this 2. On simplification, the result comes out to be minus q by 4 pi a d square minus a square cos of theta to the power 3 by 2. This is the surface density of charge. You notice that this part is positive always. This is positive. If q be positive, then the inducing charge is all over negative. Let me first calculate what are the values, its minimum and maximum values. Now the surface density of charge will be sigma at theta is equal to 0. At theta is equal to 0, this cos theta is 1, so this is d minus a to the power q 3. So on simplification this becomes minus q upon 4 pi a d plus a d minus a whole square, and sigma at theta is equal to pi. In that case cos theta is equal to minus 1, and this would be d plus a whole to the power cube, and on simplification it becomes and at the equator, that is at this plane, theta is equal to pi by 2. It is a and this is 0, so it is a square plus d square to the power 3 by 2. This is not equal to 0. You know that this is the maximum and this is minimum. So the charge, this induced charge density varies as this is the value of theta. It varies. This is sigma max and this is sigma min. And this is sigma max. So this is the variation. If we want to calculate the total charge density, then we are to integrate this charge density over the surface of a sphere. First, at the beginning we stated that here the charge density must be maximum induced charge density because this point is nearer to this. The results do corroborate with what we promised at the beginning. The total induced charge. Total induced charge is only the summation over this over. So total induced charge Q induced is equal to sigma theta integrated over the surface of a sphere. So it is surface of the sphere a square sine theta d theta d phi integrated over all space. And this comes out to be on explicit calculation. This comes out to be plus q prime is equal to minus aq by d. The total induced charge is the image charge. We have solved this problem, and the solution that we have obtained by this method of images satisfies all the boundary conditions of the system. So as per uniqueness theorem, the most general solution may at most differ by a constant from the potential that we have obtained in this method. In this derivation, we have assumed that the point where we want to find out the field lies outside the sphere. So, as per the spirit of the method of images, we have considered the image charge to be situated inside the sphere. If we want to find out the potential at an internal point, then the potential or field at an internal point. So in that case, this P is somewhere located somewhere over here, and Q prime must be located outside, because we want to find out the field within the sphere, so image charge must be outside the sphere. The boundary condition will be same. The situation is simply like this. This is Q, inducing charge is located at A. This is Q prime, and the point of observation is over here, and other things will remain the same. So come to with the same thing, we find the potential at r theta to be kq. For this point, it is r square plus d square minus twice r d cos theta to the power half, and from the for the other, the image charge, it is r square plus d square d prime square minus twice r d prime cos theta to the power half, and the potential is 0 on the surface. So phi E at r is equal to a theta is equal to 0. This is kq a square plus d square minus twice ad cos theta to the power half plus kq prime a square plus d prime square minus twice a d prime cos theta to the power half. As per our assumption, the point charge, so D is greater than A, and we are considering field for which R is less than or equal to A, so D prime is again greater than A. So we expand this in Legendre polynomial as we did in the other case is this. First term is 1, second term is a by d cos theta plus higher order terms. For the second term is k q prime by d prime and 1 plus a by d prime cos theta plus higher order terms. If we compare the coefficient of Legendre polynomial of order 0, this gives you q by d plus q prime by d prime is equal to 0. And if we compare the coefficient of Legendre polynomial of order 1, this is q a by d square, q a by d square, and from this it is q prime a by d prime square, q prime a by d prime square is equal to 0. A is non-zero, so we strike off, and q by a, this gives you q prime by d prime is equal to minus q by d. If we use this, we get q by d square minus q prime by d is q by d into d prime is equal to 0. So which leads to d prime is equal to d, and if we use this, q prime is equal to minus q. That means these 2 points are the same. So the potential within this is the combination of q at A and minus q at A also, so potential is 0. We know that the potential within a conductor is a constant, and since the conductor is a grounded one, the potential is continuous across the surface, so the potential within this pair is equal to its value on the surface. Since its value on the surface is 0, the value is 0 within, so this gives us the same result. So we conclude that put phi e at r theta is 0 for r less than or equal to A, provided so this is the result, and which corroborates with our earlier knowledge. In the next class, we shall consider the situation where the image charge is placed inside the inducing charge is placed inside the sphere, and we find out the field. Okay, let me do this right now. If we place the inducing charge outside the sphere, we found that the magnitude of the image charge is minus aq by d, and the distance is d prime is equal to a square by d. In this case, we assume that d is greater than a, that's why the magnitude of q prime was less than that of q and d prime was less than d. But if we consider the point charge to be located, this is the sphere, and we consider a inducing charge is located within the sphere, and we want to find out the field within it, and then the image charge must be placed outside, and in that case d is less than, here d is less than a, D in that case D will be less than A, and if we perform calculation in the similar fashion, only thing you need to know that the which one is the smaller of A and D. The smaller one will appear on the numerator and the greater one will come in the denominator. That is, the things will be like this, where R smaller means smaller of the two, and the greater, this R greater means greater of the two. We again land up with the same expression, as here D is less than A, you will find that the magnitude of Q prime is greater than the magnitude of Q, and D prime would be greater than D. That is to say, the image charge will indeed be outside the sphere, and we can perform the calculation in a similar fashion. So today we have considered three situations. One is that a point charge is placed outside the sphere, and we calculated the potential at an external point. Then we have also calculated when the point charge is at an external point and the field point lies within the sphere. In that case, we found that the image charge is of equal magnitude as of the inducing charge and placed in the same point, so that the potential inside is 0. And third example, we consider where the inducing charge lies inside the sphere, and the point of interest was to find out the field at an internal point. So for internal point, we need to place the image charge at an external point, and if we perform calculation as we did in the earlier case, we will end up with this result, and which says that the magnitude of the image charge is greater than the inducing charge, and the distance of the image charge from the center of the sphere is greater than the distance of the inducing charge. In fact, the image charge should lie outside the sphere, which is the manifestation of this. In the next class, we shall consider a point charge placed in front of a conducting sphere which is not grounded but insulated, and there will some surface charge will be induced, and we shall perform that calculation. And next part that we shall consider is why the name of the method of images. So we should try to explain the formation of image in analogy with the image formation due to refraction in geometrical optics.